brand new unit, completely different from what we just finished with. You're going to be like, oh, thank goodness, math is back. Transformations are gone. We're going to start this unit by studying how to simplify radicals. We're not doing that just for the sake of doing math. We're doing it because we'll need to simplify them as we work other problems throughout the year. With triangles, with quadrilaterals, even with 3D solids, we're going to need to know how to simplify a radical. So this is a skill, today's lesson, you will be using almost daily throughout the rest of the semester. So it's a very important lesson. All right, write down these two things right here. We're going to talk about the parts of a radical. What are they called? So that first one is called, so what it's pointing to, we all know and are familiar with this symbol. It is called a radical sign. I'm not calling it a square root sign on this one because it actually could be a cube root. You can take square roots, cube roots, you can go up to 4, 5. So I'm calling it a radical sign instead of a square root. Now, do you know what it's called, the number that's under the radical sign? Can you call it a house? Not technically, Ethan, you can't. What's that number called under the radical? Say it. Type it. It is called the radicand. So go ahead and write that down because I'm going to be using that word a lot throughout this semester. And so I want you to know which one I'm talking about when I say radicand. So the radicand is the number underneath the radical sign. Usually an integer underneath the radical sign. The index, well, we're assuming these are all square roots. So there's an understood 2 right here. We're never going to write that 2. But in this unit, we're not going to take cube roots yet. We'll save that for 3D solids. Okay, I kind of want to compare and contrast these two real quick. So I want you to write down x squared equals 16 and square root of 15. They actually have different answers, believe it or not. So how do you solve that first one? X squared equals 16. How do you solve it? You just said the answer, but yeah. So to solve this, we've done this since, the second week of school. You would square root both sides. Now, when you do that, when you square root an x squared, it actually produces 2 answers. We never really write this step, but the next step when solving this is x equals plus or minus square root of 16. Then x equals plus or minus 4. So a lot of us skip this step right here. That's where the plus or minus comes in. It comes in when you square root an x squared. Now look at this problem. Are we square rooting an x squared? No. That just says positive square root of 16. That's all it is. That is positive square root of 16. So the answer to this one is 4. So I don't want you to go plus or minus crazy in this unit. When I say square root of 9, I want you to write 3. I don't want you to write plus or minus 3. Now, if you're solving an equation, this is a big difference. If you're solving an equation and you're solving for an x squared, that 2 tells you there's going to be 2 answers, the squared. So that's why there's 2 answers there. So we see the difference. We know when to put plus or minus and when not to put plus or minus. Hopefully. Equal sign. The equal sign made a big difference there. When we did it to both sides, that made a big difference. Okay. Perfect squares are your friends. I want you to get to know your friends. I want you to memorize your friends. I want you to know your friends. So perfect squares, I'm never going to give you a quiz on the perfect squares. But I am going to tell you that memorizing these will make your life a lot easier and make solving your quizzes a lot faster. I know you know most of them. So if I were to quiz you on random ones, what's 8 squared? You should be able to, boom, say 64. What's 12 squared? You should immediately think 144. None of these. 2 squared? 4. None of these should you enter into your calculator. None of them. They should be memorized, part of your wealth of knowledge in your brain, I guess. 6 squared, 36. Okay, so these are called perfect squares because when we do the opposite of squaring to them, we get a whole number. So a perfect square is a number that when you square root it, you get an integer, a whole number answer. So you need to be able to go back and forth. You need to be able to square all of those, but conversely, you need to be able to square root these perfect squares. You need to be able to recognize them. So square root of 49, I know you already typed them. You should never put that in your calculator, ever. Square root of 25 and square root of 121. So memorize at least 1 through 12. If you want to go for it and memorize 1 through 20, that would not hurt either. Perfect squares. Okay. Now, here's the good stuff. Here's what we're doing during the lesson. Most of the time, the radicand is not going to be a perfect square. So when it is not a perfect square, we always have two choices. We can simplify the radical, which is what we're learning how to do today, which we're going to do, like I would say 90% of the time. Don't write that down. You're going to simplify the radical, or we can go to our calculator and we can push square root of 90, and we can get an approximate answer. This would be a decimal answer. Number 1, our answer would be exact. Number 2, our answer is just an estimate. So we would never use that in a really important situation where we would need exact answers. So there's a place for number 1 and there's a place for number 2. We'll mostly be doing number 1 because, let's be honest, we like to be perfect. We like to be exact, right? Okay. So let's get down to business. How do we simplify a radical? What is the square root of 75 simplified? Kind of reduced, but that's not the right word. So I'm going to tell a quick story to give you like an analogy. I bet you have other analogies, but this is the one we're going with here. All right. Once upon a time in a town called Neverland, the prime numbers developed an evil scheme to take over the world. So do we know what prime numbers are? It's kind of important. Okay. Those numbers for which the only factors they have are themselves and 1. They're kind of lonely. They don't have any really good factors. So here's a sampling of them, 2, 3, 5, 7. I think there's even a song about the prime numbers. You can sing a song. So the authorities took action and decided to throw all the prime numbers in jail. You're prime, that's it, you go to jail. The jails are going to be our radical signs. That's our jail. My animation's not working. But the prime numbers were too smart for the authorities. They figured out that if they could locate an identical prime twin, together they could escape jail. Yay! We're free! Yippee! They have to find a twin to escape jail, right? Those who couldn't find a twin were stuck in jail forever. Aw, shucks. Okay, so how does that work with radicals? So, you start with your radicand, and you find any two numbers you feel like that multiply to get your radicand. I picked 25 and 3. You could have picked 15 and 5, right? Totally would have worked. Okay, so you draw the branches of the tree and you write your factors. When you get to a prime number, that's why you need to know your prime numbers. When you get to the prime number, you circle it. If it's not prime, you keep going. More branches of your tree. 5 and 5 is 25. Prime, prime. So you circle it. Now, remember, if they find a buddy, they can escape. If they don't find a buddy, they're stuck forever. 5 found a buddy. So we cross it out, and we write it on the outside. 3, escape jail, they're in the real world. And then our 3 is stuck in jail forever, no escape possible. So the answer is 5 root 3. Pairs get to escape, singletons stay in jail. Okay? I want to make sure to show you that you can use all different factors, so I want to do this one again, but with different numbers. We already did 25 and 3. Let's do 15 and 5. Oh, I got a prime one, so I circle it. 15, 5 times 3, prime, prime. I look for pairs. Found a pair. It goes on the outside. Notice I'm not putting 25 on the outside. I'm putting 5. 5 on the outside. 3 never found a pair, so the simplified answer is 5 root 3. Okay, I want everyone to put that in their calculator right now. Type 5 square root 3 in your calculator. The beauty of radicals like this is that you can check your answers yourself. It wasn't so easy to do that in transformations. So I'm going to round to nearest 100 because most of the time they ask us to round to nearest 100. So when I put 5 root 3 in my calculator, I got 8.66. Now put square root of 75 in your calculator. Square root of 75. Imagine that. There we go. 8.66 again. Okay, so if you simplify it, and you put this in your calculator and this in your calculator, and you get the same decimal both times, then you've already graded your own quiz. You've already checked your own answer, and so you will know if you have 100 or not before you even turn your quiz in. Okay, let's do number 2. What factors would you like to use? What factors? Uh-oh, I was going with 12 and 10. Well, we can do 2 and 60. Do that. 2 and 60. Are there any dead ends? Are there any primes? Yeah, 2. Dead end. When you get to a dead end, you circle it. What do you want to do for 60? Oh, we're going with 2 and 30 again? Okay, we're loving 2s today. Oops, that's a 30. Dead end, circle it. I'm going to take over. 5 times 6, dead end. I'm going to go out this way. You can. It's a tree. The branches can go wherever we want them to go. Okay, guys. So, what are we looking for? Pairs. Twins. Pairs. Okay, so I'm going to find a pair. And I'm going to write it on the outside. They escaped jail. Whoa, this is weird. Do you see any more pairs? No. So all of the prime numbers that didn't find a pair are stuck in jail. 2, 5, and 3 are stuck in jail. Now what you do with the numbers left over, with the numbers stuck in jail, is, yep, you have to multiply them back together, believe it or not. So the final answer is 2 root 30. That is as simplified as it gets. They get smushed together in a tiny jail. Yep. All right. So that is the answer. The square root of 120 as a decimal is about 10.95. So we want to be able to go both ways. We want to be able to write it as a decimal and as a simplified radical. All right. Try this one, please. What factors should we start with? Doesn't matter. Any two numbers that multiply to get. Okay, you went with 60 and 2. Okay. Oh, wait. Didn't we do this one on the last slide? Oh, we totally did. I repeated myself. Can I change it? Can I change it on you? I'm going to change it on you guys because I don't want to do the same problem twice. Let's do 90. Sorry, change up mid-lesson. All right. So we had a 7 out front to begin with. I'm going to go with 9 and 10. Neither of those are prime, so we keep going. 5 and 2, prime, prime, circle, circle. 9, 3 times 3, prime, prime, circle, circle. 9 is a perfect square. Okay, so now we need to take inventory. What I don't ever want you to do is to forget about the guy out front. Forget about the guy that was already out of jail, the one that already escaped. That's really important. So first, you write the one that was already there. Then you can write the escapees. And then you can write the ones that were stuck. Final answer to the problem. You multiply the ones that escaped, and you multiply back together the ones that were stuck. So the answer to that problem was 21 root 10. Okay. What do you think of when you hear the word inverse? Inverse. Okay, we'll talk about alt codes later, guys. Okay, you hold down the alt button and you push the 3 numbers. Okay, an inverse, not a statement, no. Oh, you're thinking of, when we learn contrapositive. Okay, in arithmetic, inverse means you are canceling out an operation. You're undoing the operation. They're opposites of each other. So what's the inverse of addition? Subtraction, right? What's the inverse of division? Multiplication. Okay, so what's the inverse of squaring something? Square rooting it. Okay, so squaring and square rooting are inverse operations, meaning they undo each other. They cancel each other out. So when you square the square root of 10, the square and the square root cancel, and the answer is just 10. Should you square it and do square root of 100 and this? No, you skip the step. You absolutely just cancel them out. So square root of 10 squared is 10. Square root of 1,254 squared is? The moral of the story, when you square square root, the answer is just the radicand. The answer is not square root of 10. The answer is not 10 squared. The answer is the whole number 10. The whole number 1,254. Okay. Now, I want you to put a star in your notes by this number 12, 2 root 5 squared. I have a lot of students who skip a step here and get this one wrong. You are squaring the 2 and you're squaring the root 5. Notice the parentheses. They're not there for no reason. I have a lot of people put 10 as their answer to this one, so be very careful. You need to square both terms, or in other words, you need to square every term that's in the parentheses. 2 squared is 4. Square root of 5 squared is 5. So the answer to that problem, and you're putting a star by it because a lot of students miss it on the quiz, the answer is 20. And a lot of people put 10, so be careful. Can you put that in your calculator? Absolutely. Open parentheses, put 2 root 5. You have to exit the radical, close parentheses, and square it. So yes, you can put that in your calculator. You're allowed to use a calculator on every assignment. Okay. Now we're going to add and subtract radicals. The beauty here is that it works the same way as adding and subtracting variables. Okay? 2x plus 3x. 5x. 4x plus 3y. Well, it's 4x plus 3y. What's the difference here? In the first one, those are like terms. In the second one, they aren't. So we can't do a thing. Radicals work the same way. So if I had 2 root 3 plus 3 root 3, my answer would be 5 root 3. Those are like terms. The root 3 is treated just like x. If this was 4 root 3 plus 3 root 7, the answer would be, the simplified answer will be 4 root 3 plus 3 root 7. We are not allowed to add radicals unless the radicand matches. So, radicand must match, then we can add them. Let's do these examples in our notes. Write example number 1 down, and we're going to get right to it. We're going to start solving it. 5 root 3 plus 2 root 75. Okay. So first of all, those radicands don't match. But wait a minute. One of them is not simplified. So we need to factor tree to 75, which we did earlier in class today. Prime, prime, prime. So I'm going to rewrite that one, okay? So this is 5 root 3 plus, I'm going to rewrite this guy. Okay, there was already a 2, and then what escaped? A 5 escaped. Y'all are already answering it. Okay, there was a 2 out there and a 5 escaped. 2 times 5 is 10, with a 3 left over. I hope you're okay with what we did there. There was a 2, a 5 joined him, 2 times 5 is 10. So now we've got 5 root 3 plus 10 root 3. Now the radicands match, and we're allowed to add them. Final answer, 15 root 3. Can you put the problem in your calculator and put the answer in your calculator? Yes, you can, to check your answer. Okay, number 2. Whoa, we've got some simplifying to do. Let's do 4 times 2, prime. 2 times 2, prime, prime, prime. 8 is actually a perfect cube, right? Because there's a set of 3, but we're not worrying about that. Okay, so 5 root 8 becomes, okay, there's already 5, and a 2 escaped. So we've got another 10 root 2. Okay, now let's work on this guy. 18. 9 times 2, 3 times 3. Okay, there was already a negative 3, and a 3 comes to join it. 3 times 3, 9. What's left over? A root 2. And then just bring this guy down. You couldn't do anything with that guy. Oh, now we're talking. So we've got some like terms, some non-like terms. 10 root 2 minus 9 root 2, that's like saying 10x minus 9x. It's just 1x, or 1 root 2. So we've got 1 root 2. I'm not going to write the 1 because it's understood. Plus root 3. Yeah. So we simplified, and then we combined like terms. Okay, now we're going to move on. That was adding and subtracting. Now let's multiply. The fabulous news is that multiplying works the same as variables work as well. If you ever forget what to do with radicals, pretend it's a variable all of a sudden and you'll remember what to do. What is 2x times 3x? This is really important because it's not 6x. Yeah, this is different. It's 6x squared. We multiplied the numbers, and then we also multiply the x's. That's not how adding works, right? In adding, you just keep the x. You don't do anything to it. But you have to multiply both sets of terms. Radicals work the same way. We'll do it on the next slide, actually. Let's do this one. Are we just like not allowed to multiply them because they're not like terms? Actually, we can and should multiply them. 4 times 3 is 12. Y squared times x is just y squared. So the thing that we did here is we did the numbers on the outside separate from the variable. We were able to multiply those. We were allowed to multiply them. Let's try it with radicals. 3 root 2 times 4 root 5. These are not like terms. But what I'm trying to convince you of is you are allowed to multiply them. You can't add them, but you can multiply them. How do you multiply them? You multiply the numbers on the outside separate from the numbers on the inside. 3 times 4, our favorite number. So, square root 2 times square root 5. You are actually allowed to multiply them. So my analogy wasn't foolproof because the x and the y, we really couldn't put them together. But in this one, we can multiply them. So my analogy was not perfect. And that's our final answer. That's it. 12 root 10 is the simplified answer. You are allowed to. You do the numbers on the outside separate from the numbers on the inside. Alright. Try that first one. Let's see. Multiply the numbers on the outside first. 2 times 1. 2. Multiply the radicands. Square root 3 times square root 5. Square root 6. That's all there is to it. Okay, next one. Oh, are you allowed to multiply these? One's a radical and one's not. Yes, you're allowed to multiply the like terms. You can multiply the 4 times the 6. You will never multiply like a 6 times a 10 inside a radical. If something's in jail and something's not in jail, they do not mix. They are not allowed to mingle. So we keep them separate. 6 times 4, 24, and then we don't do anything with our root 10 because there is nothing to multiply it by. Easier than you thought, yeah. Okay. Look at this. Square root 3 times square root 3. What is that? What does it equal? It equals the square root of 9, and 9 is a perfect square. The square root of 9 is, oh, it just equals 3. But I want you to realize that when you multiply two radicals that are identical, those radical signs cancel out, and it's just like when we wrote it like this. It's just like that, where the answer is just the radicand. So never do the step of, oh, that equals the square root of 9, and the square root of 9 is 3. Skip that step every time to save yourself time. Square root of 27 times square root of 27, 27. Square root of 1,289 times square root of 1,289, 1,289. Okay, we got that under control. Next step, dividing radicals. Same as multiplying. You're going to divide the numbers on the outside separate from the numbers on the inside. 6 divided by 3, 2. 8 divided by 2, 4. Now be careful. Are we done? Is that the answer? Ooh, one more step. That's a perfect square right there. Perfect square. You never leave perfect squares alone because you're not done. So the final answer is plain old integer 4. That is the answer. 2 times square root of 4 is like saying 2 times 2. 2 times 2, 4. Try some more. You are allowed to divide the numbers if they're both in the radical. You're allowed to divide the radicand. So number 5, we've got this 4 on the outside. There's nobody to divide by, so we just write that. Now we're allowed to do square root 20 divided by square root 4. Cool. You always ask yourself, could I simplify that more? And the answer is no, you couldn't. Ooh, what about number 6? I spy something on number 6. What is the square root of 9? It's a perfect square. It is a perfect square. So instead I'm going to write 3. What happens to 3 is you use your regular division rules that you learned. Use them, put them to use. Wow, so the answer is just 35. Final answer. Okay guys, we have one more thing. If you need to leave, you can. You just need to watch this part at home. Alright. One more thing that we need to learn is called rationalizing the denominator. I want you to write this checklist down, please. Kind of, Alex. How do you know if your answer is done? How do you know if you've solved the problem? Well, first thing to check for. Your radicand better have 0 perfect squares in it. So square root of 9, that's not done. Square root of 20, that's not done because 20 has a 4 in it, and 4 is a perfect square. The second thing is your radicand is never allowed to have fractions. So you have not simplified your answer if you have fractions in your radicand, or in your square root rather. Lastly, for some reason someone decided it is just not proper to have radicals in the denominator. It's just not proper. So you're not done if there's a radical in the denominator. How do you get rid of the radical in the denominator? That's what we're going to talk about next. So I'll give you an example of each one. This one would be disobeying that rule right there. This one would be disobeying that rule right there. And this one would be disobeying that rule right there. None of those are simplified answers. None of them. So what do we do when we're in either of these situations? I'm going to teach you next. Okay. So, rationalizing. To make rational is what that means. We need to make the denominator rational. He's not rational right now. He's irrational, right? So, how do you, we're going to be like fighting fire with fire, which you're not allowed to do, right? That doesn't work in real life. But how do we combat a square root 3? Well, I know how to turn that into something that's not a radical. Square root 3 times square root 3. Wouldn't that do it? Now, the problem is you're not allowed to change the number. If I just multiply the denominator with square root 3, I've completely changed the problem. So what we need to do is multiply the top and the bottom by square root 3. That is a really fancy number 1. Does everyone agree that this is 1? Square root 3 divided by square root 3. That's 1. When you multiply something by 1, you don't change it at all. I am not changing what this fraction equals. I'm just rearranging. Okay? So we are going to multiply it by square root 3 over square root 3. Let's do the bottom first. Square root 3 times square root 3. 3. Right? We did that a few slides ago. 1 times square root 3. And I know I'm going to have a hard time convincing you, but that is the more simplified version of the one we started with. I know, it's weird. Just accept it. Sometimes math does that to us. Okay, let's try some more. Ooh, number 9. Not allowed to have fractions as a radicand. So what we're going to do in number 9 first is we're going to separate these guys. Totally legal. Totally allowed. There's no fractions in my radicand anymore. Oh, no. Now I have a radical in the denominator. So, how do I battle that? With a really, really fancy number 1. A really fancy 1. Okay, let's multiply through. Let's do the denominator first. Square root 3 times square root 3. 3. Square root 2 times square root 3. I remember from my multiplication rules, I'm allowed to multiply them. I can't add them, but I can multiply them. Okay, next one. There is a radical in the denominator. That's really the only thing wrong with this one. Everything else is nice and simplified. So, what I want you to remember is that don't do overkill. Don't do more math than you need to. To get rid of the radical, I only need to multiply by square root 6 over square root 6. I don't need to multiply by the 2 as well. So you don't multiply by the whole denominator, just the radical portion of the denominator, okay? That's just a fancy number 1. I'm not changing my problem. This is a multiply symbol. Let's do the bottom first, okay? There was already a 2 there. Square root 6 times square root 6. 6. Okay, so that's the bottom. Now let's do the top. 3 times square root 6. We wouldn't dare multiply those together because one's inside, one's outside. Okay, let's make this prettier. Ooh, we're actually still not done. The 3 and the 12, use your good old canceling out rules from algebra. 3 goes into 12 4 times. Phew. So that one had a lot of work. That one doesn't really resemble what we started with at all, but those are the same exact number, promise. Last one of the day. What I would do first on this one, every time you see ones like these, I would separate them first. Okay. There are lots of different routes to get to the right answer here. I would clean up the top first. The bottom, there's no cleaning to do because that 6 doesn't have any perfect squares in it. We're going to deal with you later, 6. We're saving you. What's true about 49? 49 is a blank blank. It's a perfect square. Okay, let's take care of that. The square root of 49 is 7. Whoa, they put a variable in there. Oh my goodness, what do we do? The square root of a to the 6. Now what I want you to remember is that pairs escape jail. If you have 6 a's in jail, do you have pairs? How many pairs do you have? 1, 2, 3, 4, 5, 6. You have 6 a's. Put them in pairs, put them in, oh, I have 3 pairs of a's. They all escape jail because there's an even number. And how many of them escape jail? 3. Just remember, radicals are about looking for pairs. Well, square roots are about looking for pairs, not all radicals. Okay, we have one more step. We are not allowed to keep that 6 in the denominator. Multiply. Denominator first, square root 6 times square root 6 is 6. And then the top, none of those are compatible. Doesn't really matter to me what order you write it in. You might want to put the variable last, but I'm not going to be really picky about that. Ta-da! That was my ta-da. Done.